Hello everyone, today we're doing concavity and points of inflection. So to start, we're going to draw some tangents for these curves. So let's see. So here's a few for that, and a couple. There's one. Another. Okay, so a function is concave up if it lies above all of its tangents on that interval, and it's concave down on an interval if it lies below all of its tangents on that point. So a point on a curve is called a point of inflection if the curve changes from concave up to concave down, or from down to up. Okay, and something that comes to mind right now, probably the easiest example I can think of is the function y equals x cubed. So it's curved down on that interval, and then it's curved up on that interval. So that's a point of inflection. Sort of the difference between that and that. Okay. So next, mark the points of inflection on the graph below. So you can see, let's just trace it. It's going up, and then it kind of stops being up, and then it goes concave down for a bit, and then it goes concave up again, still concave up, and then it goes concave down. Okay, so it's concave up from -4 to 1, as well as from 3 to 6, and from 6 to 9. Okay, something wacky happens there. And I included a square bracket there because it's a filled in circle and it seems to be concave up on that entire interval. Okay, and it's concave down going from 1 to 3, as well as from 9 to maybe 13-ish. Kind of hard to say where that ends, maybe. All right, so note, changes in concavity do not always occur at a point of inflection. So here's an example. We have a graph going concave down and concave up. So there is no point of inflection, right? At the point where it switches, it's an asymptote in this situation. Okay, so if we're given the equation of the function and not its graph, how do we know where the function is concave down or concave up? Okay, and how do we know where the points of inflection are located? So looking at the concave up thing to the left here, as you go left to right, the slope of the tangent goes negative to 0 to positive. So let's draw that. So we go negative to 0 to positive. So that's a negative slope. That's a positive slope. All right, so yeah, negative to 0 to positive. So that means the derivative, the slope, is increasing. So if we were to graph, so this is f, right? This line here. If we were to graph f prime, so the derivative, you would notice it goes from negative to positive negative to 0 to positive, so that would look like that. And if you took the slope of that slope, so if you were to do f double prime on this, so looking at the slope of this graph, that would look like this, right? Constant slope on f prime. So this means that the derivative f double prime is positive. I can't quite help but shake the fact that this looks like that guy, if any of you watch that show. But anyways, besides the point. Okay, moving on to the next one, the concave down. It goes from positive to 0 to negative. So we go positive to 0 to negative. And so as we go left to right, yeah, positive slope to 0 slope to negative slope. So if we were to draw f prime, what that would look like is sort of like that, right? So we go positive slope, right, to 0 to negative slope. Okay, and if we did the slope of the slope is constant and negative. So if we were to do that one, f double prime would look like that. So f double prime is, let me just get that out of the way. Oh. F double prime is negative in this case. So we have a way to figure out whether it's concave up or concave down. So what we got to do is take the second derivative and figure out what the sign is on a particular interval. Just for fun, that one I thought kind of looked like something too. Kind of looks a bit like a toad. Anyway, I think I'm getting a little weird, just being quarantined, sort of. So, anyways, I guess you can expect that to ramp up as we go through the semester. Okay, so test for concavity. Next page. If f double prime is greater than 0 on an interval, then it's concave up. And if f double prime is less than 0 on an interval, then we have concave down on that interval. Okay. Use the derivative to show that the function is concave up everywhere. So if we take the first derivative of this, simple enough, should be 6x plus 2. If we take the second derivative, which gives us the concavity, it's just 6. Okay? It's 6 for all x. So if it's 6, regardless of what value we pick for x, and it's positive, that means it's concave up. So if you look at, that's the graph, it's concave up, right? It's just a standard parabola. That makes sense. Okay, delete. All right, P of x. So if we did this one, I've already kind of graphed it here, as you can see. But let's take the first derivative of that. So that should be 4x cubed minus 12x squared minus 36x plus 5. So there's the first derivative. And we're looking at concavity, so we should take the second derivative. So that'll be 12x squared minus 24x minus 36. You can factor a 12 out of that, leaving you with x squared minus 2x minus 3. And points of inflection will happen when the double derivative or the second derivative is 0. We can factor this a little bit further. 12, so multiply to give negative 3 and add to give negative 2. We should do x minus 3, x plus 1. Okay. Look at the intervals. So there will be something interesting happening when x is negative 1, and there will be something interesting happening when x equals 3. Okay, we have our components of the double derivative, 12, x minus 3, and x plus 1. 12 will be positive for all of these intervals. It's just a positive number. Okay, x minus 3 to the left of negative 1 will be negative. So suppose I chose x equal negative 2. That would be negative. X minus 3 will be also negative on this interval. So if you chose like x equals 0, it'll be negative. And then to the right of 3, we're looking at positive. Okay, and then last, x plus 1 will be negative on that interval. Then it will be positive and positive. So those factors give us p double prime. So it will be positive on that interval. It will be negative on that interval, and it will be positive again on that interval. So what that means is I'd expect concave up, then a point of inflection could be concave down. I was just going to write dn, concave down, and then concave up again. Okay, so on the interval from negative infinity to negative 1, it's going to be concave up. From negative 1 to 3, it's going to be concave down. And from 3 to infinity, it's going to be concave up again. So we can look at the graph, right? Blue to front. Let's have a look. So compare to what we have written. Concave up from negative infinity to 3. From negative infinity to negative 1. Is that what I wrote? Yeah, okay, cool. So concave up to there, and that looks about right, yeah? And then we go concave down from negative 1 to 3, which is, looks right. And then it goes concave up again for the rest of it. Great, so that looks more or less as it should based on what we did with our double derivative or second derivative. Go away. There we go. Okay. Right. Example number 3. Some trig for you. Discuss on the interval from negative pi to 2 pi in terms of concavity and points of inflection. Okay, so we're doing concavity. We should take the second derivative of this. So first derivative is fairly straightforward. Negative 1/8 cos 2x times 2, right, by the chain rule. I got to take the derivative of the inside stuff as well and multiply. And then derivative of cos x is negative sine x. Okay, that is the first derivative. We should simplify that a little bit. So we get there. Okay, you could proceed with the second derivative at this point using what you have there, but I think our lives might be a little bit simpler if I get everything. So I want to get rid of any double angle identities, and then hopefully my analysis of the terms or the factors that we might end up with will be simpler. So I'm going to use this identity, so cos 2x equals 1 minus 2 sine squared of x. So that should be correct, hopefully, double check. 1 minus 2 sine squared x. Okay, fine. So that's what I'm going to use in place of cos 2x, so let's do that. So negative 1/4, 1 minus 2 sine squared x minus sine x. Okay, I'm going to, let's see, switch that up a little bit. So let's see, I'm going to multiply everything through. So, okay, I'm going to factor out a negative from there. So I'm going to go 1/4 2 sine squared x minus 1 minus sine x. Okay, and then I'm going to bring this one in as well. So I'm going to go like this, 1/4 2 sine squared x minus 1 minus 4 sine x. So notice if I were to distribute that in there, that would give me back the original. So should hopefully just make things a little bit simpler when we go take the second derivative. Okay, definitely not the only way to do this question, but hopefully that pays off. So I'm just trying it out. Okay, so we have the first derivative purely in terms of sine, which is nice, and there's no double angles in there. Okay, if I take the second derivative now, it's going to be 1/4, and hopefully you might see that our work pays off a little bit here. The derivative of 2 sine squared x will be 4 sine x, right, because we got to deal with the exponent, right? So drop the exponent by 1 and multiply out front by 2. So 2 times 2 is 4 times sine x, and then we got to take the derivative, multiply by the derivative of sine x, which is cos x. All right, and then subtract. So the derivative of negative 1 is 0, and then the derivative of negative 4 sine x is negative 4 cos x. Derivative of sine is cos. Okay, so now we can factor a 4 out of each of these things. We can also factor out a cos x if we wanted to, leaving us with, so if I factor a 4 out of each of these things, they're going to sort of cancel. 4 divided by 4 is 1. And then what I'm just left with is cos x times sine x minus 1. Okay, and that looks pretty nice. So let that equal 0. That's going to give us our points of inflection. Okay, cosine is 0 at the pi over 2. So pi over 2, 3 pi over 2, and so on. I guess we're going from negative pi to positive 2 pi, so I should include also negative pi over 2 in there. Alright, and then this one, so that should cover our points of inflection for that interval. And then sine x minus 1 equals 0, and sine x equals 1. So sine x equals 1 on the interval from minus pi to 2 pi when x equals pi over 2, right, which has already been accounted for here. So our points of inflection should be here, here, and here. So let's do that. Negative pi over 2, pi over 2, and 3 pi over 2. Okay, our factors are cos x and sine x minus 1. Okay, cosine. So think of your unit circle, right? There's pi over 2. There's the 3 pi over 2. So if we track cosine from negative pi over 2, so we'd be starting out here, so negative pi over 2 all the way up to pi over 2. That would be, okay, so to the right. Let's try that again. I'll just do, okay, so to the right, so I guess, okay, yeah, negative pi. To the left or whatever, okay, so cos would be negative on that interval. Up to, so between pi and negative pi over 2. Then we would be positive on that interval from negative pi over 2 to pi over 2. And then we would go negative again from pi over 2 to 3 pi over 2. And then we'd be positive again there. Okay, next we're looking at sine x minus 1. At best, just going to get rid of these. At best, the biggest that sine x ever is 1 at that point, right? And if you subtract 1 from 1, you get 0. So going from negative pi onward, okay, the value of sine here is 0. Then we go negative 1 at that point. So if we do negative 1 subtract 1, that's negative. So we're still negative there. And then as we go along, pi goes 0 at that point, and then it goes up to a max of 1. So it's negative the whole way through. So implications there for G double prime. It's going to be positive, right? Because negative times negative there. It's going to be negative there because those two multiply to give a negative. And it's going to be positive because negative times negative is positive. And then it's going to be negative again. So concave up, concave down, concave up, concave down. All right, let's have a look at our graph that I already did on Desmos. Let's compare to the work that we have here. Okay, so we're concave up to the left of pi over 2. So pi over 2 happens here. It looks like it's concave up there. And then going from negative pi over 2 to pi over 2, we're concave down. So pi over 2 happens here. So we are indeed concave down on that interval. And then to 3 pi over 2, which happens here, we're concave up, and then beyond from 3 pi over 2 to 2 pi, we're concave down. So you can see the intervals are good if you look at the graph. Okay. So concave down there. So and we're just looking at the at a particular interval, so between negative pi and 2 pi. So we're concave up from negative pi to pi over 2, as well as from pi over 2 to 3 pi over 2. Okay, and then we're concave down from, okay, negative pi over 2 to pi over 2. And from 3 pi over 2 to 2 pi. Alright, so hopefully that works. Let's maybe just think about that for a sec, double check. Looks like I missed a sign here. So from negative pi to negative pi over 2, good. From pi over 2 to 3 pi over 2, that seems good. And then from negative pi over 2 to pi over 2, yep. And then from 3 pi over 2 to 2 pi. Alright. Okay. Now it is your turn to have some fun with this. So for this, I would like you to do these, okay? Determine if there's any symmetry. So remember, if it's like that, then it's even. And if it's like that, then it's odd. If it's neither this or this, then it's neither odd nor even. Okay. Asymptotes, you can figure out where there's a problem. So any spots where you're dividing by 0, that might be interesting to look at. You could do horizontal asymptotes by factoring the largest thing of x from the numerator and denominator as you can. So you should get something interesting there. Intervals of increase and decrease, you're going to go find f prime and then set up your intervals, right? find any points where the first derivative is 0. Max and mins happen, so you might have, so for example, suppose you have that where the slope is positive to negative. If it goes positive to negative, that means there's going to be a max there, and then suppose maybe, just for the sake of example, it goes from negative slope to positive slope, there's going to be a min at that location. So that'll be the first derivative. Intervals of concavity, you'll do the double derivative, find out where it's 0, set up your, so there might be some, I don't know how many there are. Those will be like points of inflection. If it's positive or negative, right, you can see, all right, it's concave up on that interval, concave down, concave up, that sort of thing. Points of inflection will be same, so it'll be wherever the second derivative is 0. There may be 1, there may be 2 or 3 or so on, okay? And then sketch the graph, okay? And there's really nothing preventing you from trying this out in Desmos or on your graphing calculator, so you can work through this whole thing kind of at a very leisurely, stress-free pace, okay? Do your best, okay? I'm not looking for perfection here, but what I would like from you for this is just an attempt, okay? An honest attempt. Take a picture of your work, upload it, and we'll be good, okay? This will be due for Friday, probably Friday evening, so we can get that done before the break, and then yeah, that'll be it. Okay, tomorrow we are looking at the second derivative test, so that video will be up shortly, and yeah, that's it for today. Take care.